Professor Jan Meyer, welcome to you. It's wonderful to have you with us. I want to also recognize the head of the School of Electrical and Information Engineering, Professor Estelle Trengove, colleagues and friends. You know, these lectures are named after Bernard Price, who of course was a president of the SAIEE, was also a professor at this university, and a founder of the Geophysical Research Unit and the Palaeontology Research Unit. The paleontology one isn't that closely linked, of course, to electrical engineering, but certainly the geophysical research one has been for many years, in particular because of its real origins of the research enlightening that started taking place way back when, in fact, decades ago. But I think there's something very profoundly important about institutes like the SAIEE and universities comparing notes and joining together for joint meetings. I also do want to say that whereas I do recognize, and I must phrase this very carefully, John, whereas I do recognize a number of old friends in the audience, I didn't say that, but whereas I do recognize old friends, Pat, I also want to single out the young folk amongst us. And I think it's very important when young folk take the time and effort to actually engage with the activities of the Institute, to learn from folk who've been down this path for so many years. These are important opportunities that we don't always get in our careers. So make every opportunity to take advantage of the folk that you meet, including Dr. Nelma Wanda, who's also a lot younger than me, but I would call him an old friend. Welcome, thank you for being here. Folk, I think the other important thing is just on a very sort of personal note, it's interesting that I recall vividly when the SAIEE became 100 years old in 2009, and I'm wearing those cufflinks, not that you can see them, but I'm wearing those cufflinks this evening. This university, of course, is much younger and was 100 last year, so this is our 101st year. So Jan, it's really important, Jan, in fact, it's so significant that you have the opportunity to present the Bernard Price Memorial Lecture in the first year of this university's second century. And I think that that's particularly special. So we want to thank you very much for being available to do that for us. The other thing I want to say before I hand over to Professor Jan de Kock, the president, is to also recognize that in terms of the Bernard Price family, the house of our Vice Chancellor, Savanac, out in Parktown on the Ridge, was actually donated to the university for the use, exclusive use by the Vice Chancellor as part of the university. It was donated to the university by Bernard Price's family. And we think of that every time we go across to Savanac. And that is important because our Vice Chancellor, therefore, cannot be in any way dissociated from the Bernard Price lecture because of the association with that family. With that said, once again, welcome to WITS University. Thank you for joining us here in the Senate room in Solomon Mashlangu House. And in the case of load shedding, just hold on to somebody close to you, but we should be fine. Thank you all very much.
Good evening, ladies and gentlemen. It's a pleasure to also have this lecture here at WITS. Professor General, you may recall, presented this lecture in 2014. So, Ian, thank you very much. A welcome also to all our past presidents that are here this evening, and also to Professor Dr. Dressel, all the way from Germany. Thank you for being here this evening. And for Pia to join Jan this evening also for this occasion. I'd like to introduce Professor Jan Meyer to you. Jan and I have just spent 2 weeks in Namibia together, camping and having some good fun. He is a professor at the Technical University of Dresden in Germany, where he specializes in power quality. Those of you that have been involved in grid code compliance studies, for example, in South Africa, some of the standards originated from committees that he has chaired internationally. So Jan heads the power quality group at Dresden University, and he has a particular interest in harmonics and power quality above 2 kilohertz. Now, you might find, why is that interesting? If you look at voltage transformers, for example, they don't have a linear relationship anymore above 2 kilohertz. So when you start doing measurements, you start wondering whether you're actually measuring what is actually happening on the grid. So important work that one needs to take cognizance of when you're doing power quality measurements. Jan also works on a number of committees of the IEEE, of SAIEE, and also of European standards. So he's very much involved in the development of power quality standards, not only in Europe, but also in other parts of the world. And South Africa has been a leader in the development of power quality standards. If you think back to the development of NRS 048. So we also have a long history in power quality. This evening, Professor Meyer is going to talk to us about the challenges that new technologies bring to distribution grids. As more and more electronic equipment is coupled to distribution grids, just think of load shedding and everybody putting up PV panels on their roofs, means everybody now has an inverter in their house, which immediately affects power quality. So this evening's talk is primarily on the effects of power quality on distribution grids. We usually think of it in transmission grids, but tonight the focus is close to home. And with that, Jan, welcome here, and we look forward to listening to you this evening.
Yeah, thank you for this very kind and nice introduction. It's really a pleasure for me that I can be here, and an honor as well to be invited to give this very important lecture, especially about a subject which is somehow like a little bit a niche, or let's say the fifth wheel on a car. Yeah, nobody really wants to talk about power quality as long as he has no issues with that. And for me, it's a little bit of a passion to do power quality. So that's why it's a real pleasure to tell you a little bit about what's going on in Germany, in Europe, and what fancy things we observe in terms of power quality, especially in the low voltage networks and the, let's say, interaction with more modern appliances. For sure, all what I show you today in the presentation is not solely my own work, it's the work of our power quality group in Dresden, which at the moment consists of 8 PhD students and 2 postdocs, which do a lot of different aspects. For sure, I cannot give you all the details, otherwise we would sit in 3 days still, still here. But I will give you a little bit of a teaser about that. So I will start with a little bit of background to tell you about what's power quality, what are network disturbances, and afterwards I will tell you a little bit about the challenges that we face, and the main part will be some case studies where I will show you what happened and what was the reason for it, and at the end some final thoughts. And as it is a little bit of an, let's say, a presentation of a researcher, I will probably raise more questions than I can answer, but that's the way it is. Yeah? So let's start with general considerations. Normally what we assume is at the generation point in the power plant a perfect quality. And perfect quality means we have a sinusoidal voltage at a power frequency of 50 Hertz or maybe even 60 Hertz, and a magnitude at the low voltage network of 230 volts phase to neutral. And this is then basically transmitted, and finally it comes to the consumption, where you connect a lot of different appliances, which finally result in a reduction in this really nice sinusoidal wave shape. And this is what we call deterioration of power quality. That's what we want to characterize and analyze. So that's the reduced quality. Why do we get this reduced quality nowadays? It's especially because of a lot of power electronic equipment and appliances are introduced in the network. And here on that slide on the left-hand side, you can basically see a typical, very nicely behaving equipment, which is, for example, an incandescent lamp or a water cooker, which directly utilizes our AC voltage and does not introduce disturbances at all. When it comes to power electronics, there is a need to convert the AC into DC in order to be utilized, so direct current. Yeah? And this can be done either by classical line commutating topologies or with the new modern self-commutating topologies. And depending on, let's say, what you use, you can get disturbances that are rather in the lower frequency range, so up to 2 kilohertz, or in the higher frequency range. Yeah? And I think for everybody it's clear when you look on the left or on the right figures that this definitely has nothing to, not so much to do still with a sinusoidal wave shape. Let's talk a little bit about the disturbance mechanism, and I promise you that's the only, well, it are two basically the only scheme that I will show you so that it not gets too difficult. We can basically represent our distribution system by, now let me see if I can, I hope that is visible now, the mice, by a part that is the network side and a part that is the appliance side. Yeah? And if we assume that the network side delivers a perfect sinusoidal voltage, it has for sure an impedance. And if I connect a device which basically draws a non-sinusoidal current or a non-ideal current, you get basically a voltage drop here across this impedance. And finally, the voltage at the point of connection will also get deteriorated. And this is what basically impacts another device that you connect at that point, and that's this network disturbance mechanism. So now, one could say, well, okay, then we will definitely have no issue if we do not connect anything to the network, but this is not really what we want, yeah? On the other hand, you could say, well, if you make this impedance to 0, we would also not have something to do in the power quality community. But making that to 0 would mean infinite short circuit power, infinite short circuit level, and it's anyway not really realistic at all. So the impact factors that we have to consider is not only the emission of an individual equipment, it's much more. And that makes it so complex and maybe also keeps a lot of people away, working rather in PQ as active and reactive power than in power quality. So we have on the grid side basically a background voltage distortion that can impact the equipment connected to it. We have that grid side impedance, and on the equipment side we have, next to the active emission of the equipment, also its impedance characteristic. We will later see why this can have an impact on power quality and network disturbances as well. So let's see. Okay, I have to take this one. What about responsibilities? Yeah? It's always a hand in hand between the network operator and the manufacturers or the customers in a wider sense to maintain a reliable operation of the grid. It's not only the network operator that can manage that, it's not only the customer. There have to be basically a compromise between both of them. Yeah? And usually the responsibility of the network operator is the impedance of the network at the point of connection, and also the background voltage distortion, but this can only be properly managed if for sure also the emission is in a certain way limited, that is introduced by the equipment or the customer installations connected. So let's talk a little bit about what is quality. There is a nice definition of quality, and this is very general, says just that's characteristics of any kind of object expressed by quantitative measurable parameters, by reference values. Yeah? So what is very important is this quantitative. So you have to be able to measure it. It is not sufficient to say that doesn't look nice. Okay, what does that tell to us? We have to put that somehow in numbers. That's that, let's say, indices or the parameters. And you can basically explain that by coffee. Yeah? You will see here basically 2 cups of, I will not say that the left is coffee, the left is water. Why? I will tell you later, because this is a really nice outcome of one of our interference cases. But the quality indices for coffee are, for example, the color of the coffee, is it dark, is it not so dark, the intensity, the temperature, and so on. And in exactly the similar way, you can also define power quality. Yeah, power quality, there is even a definition in one of the IEC standards which says it's the characteristics of electricity. So the object now is electricity, which is basically represented by voltage and current. Yeah? That's why we call it power quality. Yeah? You can even say voltage quality, you can even say current quality. At a given point on an electrical system evaluated against a set of reference technical parameters. Now the question is, what are those reference technical parameters? And that people are interested, especially clients are interested in power quality since a long time, is basically shown in this little letter. It's unfortunately only in German here on the right side, which is from 1924, so from the beginning of the electricity supply, yeah, electrical networks. And it basically says, dear utility, in a little bit of a strange older German, I will say, yeah, I would like to make it clear to you that I, as a future client of you, expect only current of perfect quality. So basically that's power quality already. So the people have been aware of it. So let me see. There are many different parameters that can be used to characterize power quality. I do not want to bother you with all of them. So there is unbalance, there is the magnitude, the variations, there is the frequency itself. What I would like to focus on today, because this is also some of my main subjects, is distortion. Distortion means the deviation of the waveform from its ideal sinusoidal shape that we have seen on the first slide. And such a distorted waveform is shown here on the left-hand side in a time domain, so it's just one cycle. And you clearly see, okay, it contains next to the 50 Hertz component also another component. In this case, it's a 150 Hertz component or a third harmonic. Yeah? And we usually look into distortion in the frequency domain. So which means we do a Fourier transform, which does nothing else than trying to fit different sinusoidal waveforms of different frequency, magnitude, and phase angle to match exactly the final distorted waveform from the network. So in this case here we have a fundamental and we have a third harmonic. So that's what we need in some of the slides afterwards, where I will show you a few spectra as well. Okay, so that's maybe enough of the background. Let's talk a little bit about what challenges do we face in terms of power quality in the future or even nowadays. And you will probably see there are a few ones that are not only European issues, they will also swap over to a lot of other countries, including South Africa, all over the world. So what we see is, when we look on the grid side and the customer side, that on both sides we face challenges. Yeah? Let's mainly focus here on the appliance, on the customer side, and they are mainly driven particular by energy efficiency policies nowadays, which means we need, or there is a push to design equipment which becomes more and more energy efficient. Yeah? And we even have some, let's say, the sector coupling as one of the drivers. So we basically, on an appliance level, require new technologies. On the one hand side, reduced energy demand. Think about the lamps that we have discussed. Yeah? Switching from incandescent to LED lamp will save a lot of energy, but it introduces power electronics. Yeah? Also, the flexibility as well as the efficiency have to be further improved. And this will introduce more and more, especially modern rectifier topologies, which, for example, work with active front ends, self-commutating with active, as a PWM, active power factor correction. At the customer level, this is also very interesting development. Is one of the important developments, the energy consumption optimization, that I or you as a household want to optimize your energy consumption basically to a net zero. This is even more important probably here in South Africa in order to, let's say, bridge the load shedding a little bit. Yeah? But even for us, as we had a high increase in energy prices, especially due to the Ukraine crisis, also people more and more want to be, in a certain way, let's say, pay less. I will not say independent of the network. They want to pay less, yeah, and they want to optimize their energy consumption. This means we immediately get, especially at the household level, battery storage, which is converter, again power electronics. We get PV inverter, it's also power electronics. So we lose more and more of that direct connected grid-friendly equipment. Yeah? And that's a main and general trend that you can observe almost all over the world. Yeah? And what is a big issue, in my opinion, especially when it comes to politics, is that energy efficiency is usually only considered in terms of power frequency. Yeah? Nobody looks on efficiency in terms of a fifth harmonic. We only look on power frequency because this is what mainly causes costs, yeah? At least obvious costs. That there are a lot of hidden costs also in network disturbances is on another sheet of paper. So, and as I said, I will mainly like to talk today about the possible impact on distortion. Why do we have to talk about distortion? What are the effects? What can happen if the distortion is too high? Well, I think it's well known to most of you that we definitely have additional thermal stress, especially to shunt elements, capacitors, machines, which will finally cause a lifetime reduction. Yeah? And this can be quite significant. We can have acoustic noise due to the excitation of mechanical resonances, and who has already observed that or experienced that knows how annoying that can be. Yeah? Particularly if it occurs all day long in a lamp in the office or whatever. We even have seen it with a car charging station, yeah, with a car charger. You can have, let's say, disturbances of power line communication, which is in some of the countries in Europe heavily used for meter reading, so smart meter concept. So there the communication is in the Senelec band A, which is between 35 and 95 kilohertz. Yeah? And this can be seriously disturbed. You can have an increased load of the neutral conductor when it comes to those so-called zero-sequent harmonics, malfunction of electronic equipment, any kind, and I will give you some examples later about that. You can have flicker. So flicker, even in modern LED lamps, that was also investigated not at our university, but for example in Luleå at the university, quite detailed. Malfunction of protection devices, impact on control, and so on are even more examples. If we talk about distortion, let me systematize it a little bit. You know, we Germans like to systematize, so from that point of view, please apologize about that. But so when we look on the frequency scale, we start here at the left hand at 0 Hertz, which is the DC component. We have here the power frequency, and all the frequency components below the power frequency we call subharmonics, while all the multiples of the power frequency we call harmonics. Everything that is in between these harmonics we call interharmonics. And everything that is beyond has not an official name yet, but I like to call it supraharmonics, which has been introduced as a proposed term at one of the IEEE past general meetings. And supra does not mean anything else than beyond. Yeah? So, but anyway, if you meet someone who says, no, that has to be called higher frequency emission, or that has to be called superior harmonics, or whatever, yeah, keep the discussion down. We have much more important issues than just talking about the terminology. So I will take this term here because it's also nice and handy. Yeah? If you, for example, write a paper, and you always have to write the distortion in the frequency range 2 to 150 kilohertz. You basically have filled half of the paper if you just write it 10 times. Yeah? So higher frequency is also very interesting because it's all a matter of viewpoint. If you talk to a true EMC prof, yeah, and I tell him I talk about 10 kilohertz as higher, he said that's almost DC for me still. Yeah? So from that point of view, superharmonics is definitely something that is worth to be used. That's the emission part. We also have to look into the impedance part. So even the frequency-dependent impedance of the devices can have a major impact on how interactions will occur in the network. Yeah? Especially those grid-side filter circuits that are introduced to keep the higher frequency or the supraharmonic emission away from the network. Whilst harmonics, in my opinion, still remains important in the future, especially supra as well as interharmonics are expected to increase, and I will basically focus today only on those two just because of time. So then let's have a look now to those case studies that I would like to share with you in order to give you some ideas about what can happen. So imagine a small town, it's close to Dresden, about 7,000 is the population, and from one day to the other there have been some fancy customer complaints. One, for example, called the utility and told him, oh, well, my coffee maker is not really working properly anymore. It grinds the coffee, it throws the coffee away, and lets then out water. That's why we had this cup of water here. So even if there is a nice saying that the coffee in Saxony, that's the state where I come from, is often sometimes so weak that you can even see the pattern on the bottom of the cup, it's not that weak at all. Yeah? So definitely an issue. Another funny thing, at least if you hear it, was that the hairdresser saloon, the lady operating a hairdresser saloon, she called and said, I run crazy. My hair dryers, they switch on and off unintentionally all day long. Yeah, so yeah, I also had to smile a little bit. She could not smile at all. Yeah, you put something and then you turn it on, it turns off, you turn it on again, and then it was really ridiculous. And there was a CNC mill control malfunction in those different places that are indicated here by the numbers 1, 2, 3. So in Europe we have a standard. It's called EN50160, which defines the quality of the product electricity that has to be delivered to the customer. But this is only limited to harmonics. So the utility made a measurement and say, well, our quality complies, it's okay. So, but anyway, it was obvious that there have been malfunctions. So what was the reason for that? We did then some measurements in an extended frequency range, and what we very easily realized was that there was a significant emission here at 8 kilohertz. It was not so high, 3 volts, is something of about, let's say, 1.5%. Yeah? And this emission always occurred over the working days between 6 and 10, which suggests that must somehow be a little factory or company, whatever, around. And indeed, when we then approached this little company having the CNC mill issue, they said, yeah, because of energy efficiency, we changed our variable speed drive from a classical one to one with active front end. Yeah? And they only forgot to order the EMC filter. Yeah. So this was easily sorted out by just buying the EMC filter. They first tried it with a cheap one, yeah, but this did not work as well. So they really had to buy the one from the manufacturer of the drive in a converter as well. And then it has been basically solved, but it was quite a lot of rumors at the utility about this, because nobody really knew how to measure it at all, yeah, if we would not have been there. Another interesting story, that's the second one, is about a secretary in Switzerland. This happened in an office building, and the saying was that they recently switched to green energy. Yeah, you can even order green energy from the utility. And then certainly her computer started to make chirping noises, yeah, like a cricket. I cannot do it here, it's a little bit probably strange, but I think you can imagine. And finally, some measurements have been done by the local utility, and I will show you what they observed. So this is the waveform, and you can really nicely see how the higher frequency or the superharmonic emission goes up and down, yeah? And always if it reaches the maximum, it excites a mechanical resonance. If it is gone, then not at all. That's why it makes this chirping noise, not the continuous noise. But believe me, chirping can be more bothering than continuous. What was even more funny, I will say, how the spectrum looked like. Yeah? Jumping spectrum, yeah? Up and down, up and down, up and down. It finally was caused by 2 large UPS systems utilizing also an active front end, same make, but the switching frequencies due to the manufacturing tolerances will never be exactly the same. So you get the beating effect, which I will explain you on the next slide, where we observed something similar in a car charging infrastructure. So imagine we have a low voltage network here. We have here a bus bar or a junction box where 4 charging points with 4 charging stations with 2 charging points each are connected. And I will only talk a little bit about the current that is flowing, let's say, in the different charging points. Yeah? So you can see here the number of charging cars for the current at 10 kilohertz. It's a little bit wider, so it's a 1 kilohertz band that we analyzed. And okay, if we do not charge any car, we do not have any emission, makes somehow sense, yeah? The green one, IG, I forgot to say that, that's the current, the total current. G is a remainder from the German Gesamt, which means total, it should be E dot somehow, yeah? And the 2 different charging stations, 1 and 2 in red and blue, you can see that here. So if we connect one charger, yeah, so that's a particular type of EV which has a quite high emission, you have a 1.5 amp at 10 kilohertz flowing into the network. So we don't talk about milliamps or microamps, it's really 1.5 amp. What was even more interesting is, as soon as you connected the second one, yeah, you got less current flowing into the network, but a current of 4 amps flowing between the cars because of the impedance configuration. The impedance of the chargers is much lower at that frequency than that of the network. And usually I say current is like students looking for the shortest way. Yeah? Then it will basically flow to the other charger somehow. Yeah? While emission limits are still under development, so we expect a first standard for emission limits, I would say end of the year, but we always have to be careful with such, let's say, assumptions. Yeah? This is somehow like when you look over time of the, on the, let's say, magnitude of the 10 kilohertz emission. If you have one charger connected, you see it's rather fairly constant. As soon as you have two, you see this up and down, which is again that beating. Yeah? And you can basically determine the difference in frequency between the two switching frequencies just by the cycle of this. So this is a cycle of about 2 seconds. So we are 0.5 hertz different in the different switching frequencies in the two chargers. Yeah? As soon as you connect 3 chargers, well, it gets then slowly a mess, and if you have a lot of them, then it always averages somehow out. How you can imagine it in frequency domain is if you think in phasors. Yeah? One of the phasors, if you keep it fixed, at that's the switching frequency of the first car, the other one will, now it's difficult from, let's see, will slowly turn, yeah, will slowly turn with the difference frequency. So at one point it will be opposite, so then we have, let's say, the minimum. One time they will be both in the same direction, you have the maximum. That's the idea behind that. Okay, let's talk about another fancy or funny thing. That's a utility in Bavaria. It's another state in Germany that got a complaint from a customer that he is bothered when he wants to sleep by an audible noise from a fast charger close to his window of the sleeping room. So you see this apartment house here, and I guess probably he was, let's say, the sleeping room, one of those windows. And it was, in fact, basically here a junction box at which a fast charging station has been connected, and that made at certain times a really annoyable noise of 10 kilohertz. Okay, so the network operator went out measuring. They already had equipment to measure the higher frequencies, the supraharmonics. They measured at the transformer station, and they measured at the junction box. And what they realized was that under specific circumstances, so which means you have a specific type of car here at the transformer station in slow charging, so it's an onboard charger, and here the fast charger was in standby mode, that then you had about 4 times higher 10 kilohertz emission at that point, at the end, than here at the beginning where the emission has been introduced, which was really, let's say, ridiculous. Nobody really thought about that it can get higher when you get away from the source. They asked us to investigate that a little bit and find the explanation. And what we did was we basically did a propagation measurement. So we basically went with a generator that could generate a frequency, a variable frequency, and we injected basically here at that point at the transformer station, and we measured at the same time here at the transformer station and the junction box, and could really see this amplification characteristic. Let me show you the measurements. So this fast charger, in fact, had 3 operating modes. It could be disconnected, it could be in standby mode, in idle mode, it could be in charging operation. And we basically put it in all those 3 operating states and did this measurement, what I explained to you, injecting something here at the junction box and measuring voltages at the transformer station and the junction box. No, excuse me, we have injected here the transformer station. This is a wrong figure from the measuring the other way around. If you basically inject something here at the junction box, it will mostly, let's say, a short circuit here at the junction box. It will not propagate that far upstream. But the more important or the more interesting was the downstream propagation. So you can see here, the theory is okay. If I have an open end and I inject something at the beginning, it's exactly the same at the end, which makes in a certain way sense. Yeah? If the fast charger was in standby mode, you can see that there is really, that's the red one here, an amplification at 10 kilohertz and at 20 kilohertz again. Yeah? So it was just, let's say, a bad accident that this EV that has been connected at the transformer station here at that point had an emission at 10 kilohertz. Yeah, a resonance is nothing bad. You just not have to excite it. Yeah, that's the point. Yeah. So what we did is we tried to model that. That's why this is the second equivalent scheme that I have in the presentation, and it was fairly simple. We just needed to model the line with the inductance, so no fancy high-frequency model of lines and couplings and whatever, no. You just needed the inductance of the line along with the capacitance of the charger at that frequency, which formed a series resonance. And here you are in the middle of the resonance, and you get this series resonance amplification. This is something that has not been considered in the standardization up to now at all, because the manufacturers usually say at the higher frequency, they sort out even in the same installation or at the neighbor, but it will never propagate far. So we always thought that is true. No, it is not. Upstream, yes, but not downstream. So in low voltage networks, if you introduce something at the transformer station, you have to expect that you get amplifications downstream which can cause disturbances or interferences. Let's look on the next one, case study 4. That's in the harmonic range, and it's about instability of solar inverters. What is the basic condition? So we have a farmer, and usually those farmers, that is also in Switzerland, had a large shed. And if I have a large shed, I can put a large PV installation on it. And often those sheds are, let's say, a bit distant from the transformer station, which means you have a rather weak grid. So he installed its PV installation, connected to the grid, and was really disappointed that he often tripped with overvoltage, which is fairly clear because of the high impedance of the network at the connection point. Okay, the network operator wanted to do something really good to him and installed a series voltage regulator, yeah, which is somehow equipment that basically steps the voltage a little bit down so that there is more that can be injected by him. What finally happened is that he did not trip with overvoltage anymore, he tripped with excessive harmonics. He said, well, that was not the solution that I wanted to have. Why does this happen? And this is basically what happened was that due to the series voltage regulator, the impedance, not at the power frequency, but at a higher frequency or at a harmonic frequency, you can see it here in this little figure, at 350 Hertz has been changed in a way that it adversely interacted with the control of the solar inverter. And it finally caused the harmonic instability and the inverter tripped. Luckily, not all the inverters have such, I will say, inefficiently designed controls, but you really have to take care of that. Okay, let's talk about the next case. This is about energy optimization, often also called prosumer households. Yeah? And along with a research project that we do on updating the flicker meter algorithm, we also had to set up such a prosumer in our laboratory. You can see how this is composed. There is a grid emulator. You can see that here. It's basically a programmable amplifier where we can set different distortions, different impedances, whatever. You basically have then a bus bar where we had connected a battery storage system, a PV inverter with a panel emulator, yeah, so that the students can also work during the night, yeah, and not rely only on the day. And we had some equipment connected, which you typically find in a household, yeah, so kitchen, living room, other equipment. And you have a power manager that manages the power in order to basically bring it to net zero. And we wanted to see what is the impact of that on harmonics, on the total harmonic current. And we did a few of measurements. I do not want to share all of them with you. I will just show you the results before we discuss a little bit about what that means. So please do not be confused by the lot of curves here. So let's have a look. The blue one is the sum. And you see the sum here is mainly at 0 for the active power. This is active power, yeah? Except of some sudden, let's say, spikes or peaks, which are simply caused because of the delay in the control of the power manager compared to when you switch something on. This is very interesting because this can cause additional flicker. You see in yellow here, that's the PV, which slowly gets down because it's evening, yeah, somehow, so it's an afternoon, evening scenario. You have the battery that has to compensate for sure the power consumption of the loads, which are here in red, following a particular scenario that has been designed, yeah. So what we can see is over the whole time, most of the time, let's say it that way, we have a net zero in active power. So finally, the meter will not count anything for that household customer, yeah? That's what you want. If we look on the reactive power, it looks already a little bit different, yeah? There is still a certain reactive power, but this is not counted for the households, yeah? And what is even more interesting, if you look on the total harmonic current, you can see that it is the sum is the blue one. It is even slightly higher than what the loads only produce alone, which would be the classical customer. Yeah? And there is nothing at 0 at all. Well, you can say, okay, what does that mean? Well, it first of all means somehow like that the utility is now the garbage bin for all that what is emitted by the household, because it does not pay for energy anymore. What is the scheme of that in the future? Yeah? Do they have to pay for cleaning or whatever? Yeah? So that's on one hand side, which is probably quite interesting if this, let's say, comes more and more. The other thing is that we usually allocate emission limits for devices or customers based on its rated power, based on the power. Yeah, because it's fairly the way that if I have a 630 kVA transformer, yeah, and this is fully utilized, then I should meet the global contribution somehow. And then the one that basically has higher power connected, higher contracted power, he usually pays more. That's why he should also get more emission. But if I have no energy that I consume, I should also have no emission. And that's maybe a little bit strict, but formally it should be that way. Nobody really looks into that. And there are more and more installations. This is just one example that's coming up. For example, peak shaving with battery storage. So we have, let's say, a fast charging infrastructure that's another example, I do not have it in the slides, 480 kVA charger, yeah, at a 630 kVA transformer, which is already utilized to a 400 kVA. So they had to put the battery storage in order to get down the peak demand. But they emit with all of that they have in. So that's something, that's why I say I will probably raise more questions than I answer. How to deal with that in the future? Yeah. Okay, last case study that I would like to share with you is now becoming independent of the grid. Islanded microgrid. We did a nice project together with the university in Bogota in Colombia on that, such a bilateral project. We basically also set up in the laboratory a configuration where we can mimic an insulated or the islanded microgrid, that's that one, ISM, islanded mode, and interconnected mode. So the islanded mode was in fact the battery converter, the PV inverter, full stop, yeah? And the interconnected one was basically formed by the grid simulator and the reference impedance, and a little bit of background voltage, yeah? What you usually have from the network. Then we just connected a few household loads here in different scenarios. The first scenario is classical power electronics, which is mainly the line commutating one. Second one is modern power electronics, that's all that self-commutating one, which emits more in the supraharmonic range. And L3, we will not look into that too much, is so passive equipment, no power electronics, and the mixed one. You can see here again the difference between load scenario 1 and 2. This is one with the classical power electronics, clearly non-sinusoidal. Here you have somehow like this more or less sinusoidal shape with this little noise on top, which is the supraharmonic emission. Let's look now on the results in terms of harmonic voltages and currents at the connection point of those loads. And let's just look to the, let's say, first two scenarios. If we have, for example, the classical line commutating equipment, you have this lighter one here, lighter red one is the islanded mode, the darker one is the interconnected mode. The harmonic emission is higher in interconnected mode. Yeah? It's clearly, you can clearly see that here. Yeah? So which we could say, well, that's not bad. Yeah? So the emission seems to be lower in the islanded mode. But if you look into the voltages, you easily see that the voltage exceeds the compatibility level, which is here in the dashed line, shown by the dashed line, by far. Yeah? We have a third harmonic of 11%, we have a fifth harmonic of 11%, just by connecting a few line commutating equipment. Now we can ask, why does that happen? It's an impedance issue. It's really an impedance issue. If you look here on the right side, you see the impedance in islanded mode and the impedance in interconnected mode. There is almost a factor of, let's say, 10 in between. In particular, at about, what is that, it's about 0.4 kilohertz, so 400 hertz roundabout, you have an impedance of the network in islanded mode, which is basically formed by the grid forming inverter, of almost 100 ohm. Yeah? So you could really only connect a few compact fluorescent lamps, and then you already exceed the compatibility level. So what does that mean? So first of all, we should maybe think about that emission limits, especially for customer installations, are also based on short circuit power. Yeah? Maybe the one or other know that the short circuit ratio is somehow like what usually decides about that. So short circuit power in an islanded network, the first question is, how is that defined? Is there any short circuit power at all if I have 100% power electronic based generation? And how do we need to interpret that? And the second is, if we talk about grid forming, again the issue comes up. This is only, the thinking is in power frequency. not in higher frequencies or in harmonics. So grid forming must really be thought or has to consider the whole frequency range. It should really behave then either like a traditional network, or we need to, let's say, introduce a completely new EMC framework on that. Okay, good. That brings me to the end. I do not want to bother you more with case studies, to some final thoughts. So what we can summarize is that modern power electronic equipment, new customer control schemes, alternative grid solutions, yeah, require, in my opinion, really a rethinking of classical approaches how to manage power quality, how to set emission limits. But this is politically really stuck because the manufacturers don't want to have anything changed somehow, especially in the ISC committees. And imagine you have maybe 2 utility representatives sitting in opposite of 10 representatives of the industry. It's very difficult to discuss in that point, yeah? So what we have to do and what we try to do is create awareness and standardization for many different aspects. One in particular, in my opinion, is we have to think more about impedances. Do we need in the future also regulations in terms of how the input impedance of equipment should behave? In Switzerland, they do that for the railway system. Yeah, they don't accept any locomotive that does not behave passive up to the first resonance of the Swiss railway grid. If you discuss that with a industry representative, it's very dangerous. I know that. Yeah. Maybe we need also to create awareness at the utilities to maybe think about including power quality also in the planning. We had a really nice example where a new network has been planned from scratch, and then they immediately exceeded the 15th harmonic voltage. And the planning engineer, he did it 40 years. I think, it never happened to me. What did I do wrong? But they usually plan utilization of the lines, voltage drop, nothing else. And last but not least, awareness in politics, especially in terms of that efficiency, should not only be thought in terms of the 50 hertz, but also in the way of grid friendliness. Yeah? And we need definitely much, much more research on that. However, we should never use power quality as an excuse to block new technologies, to scare people. Yeah? If you say, oh, that can have, nothing will work anymore, operate. That doesn't make sense at all. But we also should not forget it. Yeah? That's what usually happens. Everybody thinks in power frequency. Nobody really thinks in power quality. That usually comes up later. We always have to consider coexistence of old and new. And due to the lack of a nice photo, I use this one where you maybe can see that even in, let's say, under aesthetic aspects that should be considered. So those CFLs in this nice and elegant candelabra is not really nice in my opinion. And last but not least, always think about how much is needed, not how much I can do. So this is a nice example from one of the solar farmers, you can almost say. Yeah? He switched from normal farming, yeah, agricultural farming, to solar farming with his plot, and he put solar panels everywhere, yeah, where he could do. Unbelievable. I saw that when we did skiing next to our place where we live. Good. So that brings me to an end. Thanks a lot for your attention. I hope there have been some nice and interesting ideas for you to follow up, and yeah, feel free to ask questions. I think Jan will moderate that.
Professor Meyer, thank you for some very thought-provoking examples that you can think about. Now we'll take some questions from the floor. Yes, sir.
I'm Charles Roycroft. I have a question on the solar. Something came up recently. the more panels that you are installing for a solar array, PV array, does that change the phase angle and thereby worsening the power factor? Is that something that you know about?
So we usually do not look at power frequency stuff, but normally you have the more solar panels you have probably also more inverters, but then it's a matter of the inverter control. So you can definitely have a very good power factor. Sometimes you intentionally have a power factor that compensates, for example, the voltage rise, so that you also, let's say, consume a reactive power. That's also possible. It's all a matter of the control scheme, and for sure the size of the installation. But I would not say by nature that the power factor will drop when you install more panel or more, let's say, in inverters, in my opinion. Yeah.
Any more questions? Second question? While you're thinking, Jan, a question from my side.
Yes, please.
Previously, power quality standards measured power quality up to the 40th harmonic. And you find that inverter manufacturers then had their switching frequency at the 50th harmonic. And now power quality standards have changed to measure up to the 50th harmonic, and inverter manufacturers now put their switching frequency at the 60th harmonic. So we're just playing catch up. Do you foresee any way that one can manage this process rather than playing catch up to say, let's look at a far bigger spectrum of harmonics, super harmonics?
Yeah, definitely. That's a good question. And indeed, the measurement standard 61000-4-30 in its next edition will have an informal annex which explains a measurement method for the frequency range 2 to 150 kilohertz. Unfortunately, this is a very complex one because they just overtake the CISPR 16 measurement methodology, but there you have at least a measurement method. And the emission limits are basically also based on the same way of measurement. So I think up to 150 kilohertz we are set, and above 150 kilohertz anyway you have to comply with the CISPR limits. So this should hopefully be sorted out, that they cannot, let's say, slip through again, like you say. There are even more examples of that.
Thank you. Yes, sir.
Thank you very much for a very wonderful lecture. I often say that as engineers, we will not be judged by how well we articulate the problem, but also by how much solutions we bring. So when I look at the problem that you presented on, especially looking at the high frequency harmonics, one goes into a mode of thinking of this could be a very simple solution that one can bring just using a filter. So why can't we just use a filter, for example,
Yeah, you basically can use a filter for sure, yeah. But especially if you have the downstream amplification, you really do not know where the resonance amplification will occur. So do you want to install a filter at each of the customers? So the problem is really in this higher frequency range, you hardly probably can use active filtering at all, at least above 10 kilohertz or something, so you just have to put a passive filter, yeah? But the passive filter will again then change your network impedance. But for sure, you can do it. That's how EMC filters work usually, yeah? But normally, this is not per se included, which means you experience in the first sense such a strange phenomena. And as a utility, then you think about, okay, what happens here? Is this my responsibility? Is this another one's responsibility? And the first step now is regulating emission at all, because there is no regulation of emission at the moment in this frequency range yet. Yeah.
Thank you.
Yes, John.
In terms of product standards, so it sounds like they're fairly deficient. So what is the status of product standards in terms of emission? And all this equipment like LED lighting, it's a pretty nasty way.
So in fact, for LED lighting and for the induction cookers, there are already CISPR standards available in the frequency range between 2 and 150 kilohertz. For all the other equipment, the standard is currently under development in a joint working group between CISPR Edge and ISCS C77A Working Group 1, which is the one responsible for harmonics somehow. And this standard is, as far as I know, fairly mature already, so they are close to a first CD that is published, so we will get something in the, I would say maybe next year on that. So this is definitely on the way, product standard. There's another question over there.
Yes. Before you ask the next question, if you don't mind just using the microphone, then we can also record the question.
Just as a follow-up to recognition, I think the synovic bands protect certain frequencies of electronic music. Between 150 to 500, it's a Wild West, especially for power inferior meters. Is the new standard going to protect power inferior meters going forward?
If I understand right, you talk about power line communication in the band between 30 and 95 kilohertz somehow, yeah. But that's a really delicate issue, because this was politically very sensitive in terms of setting the compatibility levels. So I think it took 3, 4, 5 years until the compatibility levels have been negotiated in order to have a certain signal-to-noise ratio, or a difference, yeah, between the intentional emission that you want for the meters and the unintentional one. Yeah? Because industry representatives did not really understand, why do you need to use the power line for communication? Yeah, we want to use it for energy transfer. So that was always the argumentation. But those compatibility levels are set and released. 61000-2-2 is the standard, yeah? And they, let's say, maintain a certain signal-to-noise ratio between the unintentional and the intentional emission. However, what is not really covered up to now is the impedance issue. Because all the equipment that you have, I can show you a frequency scan of a solar inverter, for example. They have in the frequency range between 30 and 90 kilohertz impedances that are far lower than 5 ohms, which means you get then your power line communication signal short circuit. Yeah? And this is something that is unfortunately not yet considered. And there are a lot of, I will not say a lot, but there are a significant amount of issues with meter reading in different countries of Europe. It depends also on the way what you use as the protocol. That, for example, also the changing impedance. So you have to imagine that the impedance even changes within the half cycle, yeah, because of the line commutating equipment. If the bridge conducts, you have a capacitor connected. If the bridge not conducts, you have infinite impedance. So the impedance even changes. And this distorts also those signals, even if the impedance is okay. Yeah, so there are quite a lot of additional effects that are beyond just coordinating emission limits and disturbance levels, unfortunately. But in general, it seems to work out fairly well.
Yes, just activate your microphone.
It's even more difficult to understand.
Good evening, everyone. Thank you for your presentation.
Pleasure.
So my question is not too technical, but rather it's based on the state of power quality in South Africa and how actually young people can contribute to related issues and opportunities. So number one, okay, in terms of policy and regulation, what changes of improvements are needed to ensure a better power quality in South Africa? And how can young advocates be part of this process? Secondly, with the growth of smart grid technologies, how can the South African youth actually prepare themselves for careers in this evolving field? And what opportunities does it actually present for addressing power quality challenges in our country? Thank you.
So, well, the first question was about policies in order to maintain, manage power quality, if I remember right. So, from that point of view, well, what you have to do is you have to set reasonable standards in terms of, for sure, emission limits and coordination of emission in terms of meeting the overall goal that we all have, which is EMC, electromagnetic compatibility. Yeah? And I think there are quite a lot of good standards already introduced. Maybe what I raised as one of the issues, thinking about impedances, thinking about source identification is something that needs definitely more research, where also young researchers has to be involved. Yeah? They can develop new methodologies, but you always have to take care that this not goes too much into theoretical basic research. It really has to be something that can also be finally transferred into a power quality instrument, for example, which really has practical sense and everybody can benefit from. Yeah, that's very important. And they're often sometimes the more simple things are the better ones. Yeah, it not has to be too fancy somehow. Yeah. So, and all the other things in terms of policies, as I said, it might be useful to convince the politics that there is a little bit more beyond energy efficiency in order to become robust or grid-friendly. But this is a challenge. I'm not sure if we can achieve that at all at any time, yeah? Because it's even very hard to explain politicians what power quality is. Yeah? There was even a nice story where one of the more technical participants in such a discussion said, but guys, wait, there is still Kirchhoff's law. And then one of the politicians said, yeah, well, laws are there to be changed. So, so what was the second question about? I have talked to.
Okay, so the second question is about the growth of
smart grids.
Yeah, smart grid technologies. How can the South African youth actually prepare themselves for these careers in this evolving field, and what opportunities does it actually present towards addressing power quality issues?
Okay, so definitely smart grid is a very general term, yeah, which involves or covers many different technologies somehow. Yeah? And I think there are plenty of opportunities in those different technologies to do research in, to understand them better, and even if mainly, for sure, the management of a reliable operation in terms of power frequency is what is in the main focus. You might always, let's say, push a little bit in the direction, but what about network disturbances? What about power quality? as I have shown, for example, for this energy optimization household. Yeah? And this is what basically we always have to encourage, especially students, young people, to develop a little bit more holistic view on things. Yeah? That's very important in my opinion. Not just be too narrowed, but also think about what is the effect maybe in this direction, what's the effect in that direction. So this more general holistic thinking is something that is, in my opinion, very important to be developed, especially in the younger generation. Yeah?
Let's take a final question. Willie, Jan Aram. I think let's stop there then.
Okay, perfect.
I'd like to now call on our Junior Vice President, Bruns Madiba, to present a vote of thanks to Jan Meyer.
Thank you, Mr. President, and to the past president of the SAIEE, our office bearers, our SAIEE members, ladies and gentlemen, and to our guests this evening, Prof. Jan Meyer. It is an honor to be doing a vote of thanks on behalf of the SAIEE, and I feel that I'm not really fitting into these shoes. I must admit, when I looked at your name at first, because Jan Meyer is a common name in South Africa, I then made an assumption that you are South African. Then as I went through your CV, I was still looking for a South African reference there. But then you spoke, and I'm like, there's no way. So, but because you are a nice nation, and because you've left us with homework, we're going to adopt you and make you familiar face within the SAIEE so that we can then continue with the research questions that you left us. I must say it is a privilege to have someone that has much influence through the work that you do nationally and internationally with your power quality standard development work that you have been involved in. Had I known the quality index of a coffee and its relation in my university years, and I wouldn't be an electronic engineer today. You have made it such interesting to understand what power quality is about, and we can invite our politician then to sit with you and have this conversation. Going back to your presentation, I think looking at the landscape of where we are within the South African network, we might not be at the rated penetration of renewable energy might not be the same when I look at the European and the American networks to where we are within South Africa. But a lot of what you have raised is some of the issues that within the power utilities, they're raising the same questions. Hence, I'm saying that we need to make this relationship a more familiar relationship that we can then resolve some of this. Looking at some of the issues around the grid balancing, the grid friendliness that you have talked about in terms of how we balance network, the solar penetration within the South African network, the constraints of our system and network as well that we are grappling with, the grid forming as well. We have also, from the distribution side, looking at the microgrids, which is one of the ways in South Africa that we are looking into to move power quickly to the other parts of the country where they haven't had power. But what are the opportunities within those, as much as we've heard from the questions that were asked, in terms of how do we then, from a South African perspective, take these lessons and bring them home? Hence, I'm saying that even if it's through lecturers that we can then organize and take some of the case studies and bring them back to the wider SAIEE members, bring to our utilities for discussion, our municipalities as well, when we look into the network constraint. But the important part, I think, also from a South African perspective, we are more and more seeing a consumer interest in terms of providing their own power, understanding the impact of that on the network, and also how they can best benefit from the network instead of just waiting for the South African utility to be the power provider. So these are interesting topics that we should keep challenging ourselves on. The case studies you provided were practical, and like you said, a good lecturer will always leave you with homework that we should look into. So we are looking forward to that continued relationship. I think a question was asked around the state of the power quality in South Africa and the policy and regulations, which means now also from the SAIEE, as we engage further and have this, that we bring the policy makers into the room, that we make them understand and bring them a cup of coffee as we're having this discussion. And thank you also that you have taken time to come to our beautiful country, and hoping to see more. And as much as you have said, it's a few students that you have brought along. So to our president, there are lecture themes. You said about 5 doing PhDs. How many? 8 doing PhDs. So already we are struggling with our, what now, articles. There they are. We've got 8 that are in the pipeline that we are going to have lecturers with. And on that note, I would like to give you a token of appreciation from the SAIEE.
Thank you so much. It is really a great pleasure to be here in this beautiful country. We really enjoy it. It's not the first time that I'm in South Africa.
Take the opportunity to thank Professor Jandrel and WITS University as co-hosts for this evening. And please join us outside for some refreshments. And a very important part of being together is to create or develop new friendships and talk about issues that are close to one's heart. So please, over some food and drink, build new relationships and enjoy the evening with us. Thank you very much.